So I guess if you are ready, Joris, we can start. Do you agree?
Okay.
Thank you very much for accepting the invitation. Today we have J.Bierkens with us. Joris has worked on MCMC sampling, on particular developing efficient MCMC algorithms. So it's a pleasure that he is going to present with us today about developments in piecewise deterministic Monte Carlo. Joris, you may start.
Yes, thank you very much for the invitation. So I'm really happy to present to you this work. The way my computer is now set up, I cannot see any interruptions or hands raised or so. So please.
Okay, I'll let you know in case that in case of any hands raised or so.
Yes, thank you. And then also, so yes, this talk is going to be about piecewise deterministic Monte Carlo, and so this is an innovation of the past, let's say, 8 years or so in the field of Markov Chain Monte Carlo. So I'm not completely aware of how familiar your group or the people attending are with the topic of Markov Chain Monte Carlo, to be honest. And I realized at a late stage I didn't have like a very introductory slides, but I hope it will become clear.
Yeah, no, it's about that. You can assume, if you just give us some introductory slides, it will be fine, I guess.
Yes, yes. Okay, so and my plan is for this lecture to, I don't assume that people know anything about piecewise deterministic Monte Carlo, so I'm going to explain this. And so a part of this talk will actually be a kind of introduction, tutorial style, and I'll also discuss then in the, let's look at the outline. And so the research that I'm talking about is with these people, but also some others. So not everybody is acknowledged in a good way in this slide. So let's skip it. But this is certainly work with together with Gareth Roberts and also with Kengo. We have done some theoretical studies, and Pierre, and yes. But there are a couple of people missing on that slide. Okay, so but here is the outline of the talk. So I'm going to talk about the zigzag process, and in fact other piecewise deterministic methods. So they are, yeah, as I said, an innovation of the past 8 years or so, and they all fall within this class of piecewise deterministic methods, and I hope it becomes clear. So, and one of the nice things about these processes, and that is the second, I'll go into a little bit of detail, is that you can use subsampling with these methods. Okay, I will explain it, and then the final part of the talk, I will discuss a little bit recent paper that we made available, and it's about the topic of federated piecewise deterministic Monte Carlo. So basically, the beginning is a very general introduction, the first two chapters, let's say, and then the final one is recent work. Okay, so what about this zigzag process? So, maybe first of all, to put in the back of our minds, what is the goal? Suppose we are Bayesian statisticians, and so we have some complicated posterior distribution, and it is so complicated that it's difficult to compute actually expectations with respect to this distribution, and so we wish to generate samples from this distribution. So that's what is the goal of Monte Carlo. It's the goal of Markov Chain Monte Carlo, and it will be the goal of the talk of today, to generate samples from a complicated target distribution. Okay, and we're going to use this zigzag process. So what is it? It's a continuous time Markov process. So this is already different from traditional MCMC methods in the fact it's continuous time. Whereas, you know, the Metropolis Hastings algorithm is discrete time Markov chain, and here we are talking continuous time. So time is running in the real variables, and there is a position process x, and there's a velocity process v. And maybe you can think it's, in a way, in spirit, there is some similarity with Hamiltonian Monte Carlo in that sense. Hamiltonian Monte Carlo also has a velocity. Okay, for the zigzag process, we assume that, and this is a one-dimensional example to start with, we assume that the position takes its values in the one-dimensional real axis, and the velocity is simply -1 or +1. So we move in this direction, -1 or +1. So that means that at all times the position is equal to this value. And again, it is defined for all continuous time variables. And then the velocity can change sign, and this happens according to some random, according to some rate, which depends on the position. So the first time at which a switch happens is given by this expression. So you see here that, okay, given the velocity, the position is completely fixed, but the velocity depends on some rate lambda. So that lambda really determines what will be the behavior of this process. So also, if we want to simulate from some target distribution, the information of the target distribution will be encoded in this intensity lambda. Okay, and here you see a simple example. So on the horizontal axis, we see the time, and on the vertical axis, we see position x. And you can read off the velocity. Of course, we're going up here, and so this velocity is +1, and then we're going down -1. And you see at these times, they are random times, the velocity changes. So I hope that's clear, and I also hope that the goal is clear of MCMC, that we want to simulate some target distribution. And in fact, here the target distribution is a one-dimensional standard normal. So you see, in some way, I didn't explain yet how, but we have chosen this switching intensity lambda, so that the stationary distribution of this process is a standard normal distribution. So if you would collapse the entire path on the vertical axis, on the position axis, it will be a kind of a histogram which would be close to a normal distribution. So how can we choose this switching intensity? Okay, so suppose pi is my target density, and log pi is the logarithm of that. So in the Gaussian case, that will be a quadratic function, and I call potential u. I call this negative log density. It is just because it's easier to work with negative log density than the density itself. So I call this potential function. And then this distribution pi, this density pi, is a stationary density for this process that I've just described, if and only if the switching intensity is related to this potential function in this way. Right, so there you see how the condition on the switching intensity is to have the correct stationary distribution. But here it's still implicit, because it tells you what should be the difference between the switching intensity in the positive direction and the switching intensity in the negative direction. But when you think about it, you can rephrase it to this equivalent formulation, that the switching intensity should have this form. So I take, depending on the velocity, it is +1 or -1. I multiply the derivative of u with this velocity, and I take the positive part of it. So if it's negative, it's truncated to 0. This essentially determines the correctness of the stationary distribution. And then actually I can add almost any function which depends on x only, and so the important thing is it doesn't depend on the velocity. Right, so this thing generates switches at a certain rate which depends on the target distribution, and this also generates switches, but it doesn't distinguish between whether I'm going in plus or minus direction, so it has a a net zero contribution to the stationary distribution. So I mentioned already example of a Gaussian distribution. So let's look in detail. We have a potential function, which as I mentioned, is quadratic function. And this is with a variance sigma squared. So you see that this derivative, which appears in the rate, it's linear in x. And it's also still determined by the variance, the target variance. And then in this simple case, the switching rates become these functions. They multiply the position by the velocity, take the positive part and divide by the sigma squared. So you see that if sigma, for example, is very large, so you have your target distribution has a very wide, you see that the switching intensity becomes very small, and this makes sense. So you start moving in a certain direction, and the switching intensity is very small, so you move very far until you want to switch. But if you move out into the tails of the distribution, the switching intensity becomes larger and larger, and at some point you really want to switch, and you're going to switch. And so that's, you see that in the also intuitively the switching rates do the right thing. So I hope so far that's clear. Then we can extend this to a multidimensional case. So we have a target distribution on RD, let's say, and we still write u of x for this negative log density function. But now the set of directions has changed. Before we only had velocity in one direction, now we have it in all d directions, but still restricted to this finite set. So in total there are 2 to the power d possible velocities. And now it turns out I need to satisfy a similar condition as I presented on the previous slides, but it turns out that you can choose this type of switching intensity, where this is for complete generality. Gamma actually may depend on v, on the velocities, but the ith component of gamma may not depend on the ith component of the velocity. That's all. So what do we see here? We have the partial derivative of u. So if in the ith direction we are increasing the potential, so in other words we are moving into the tail of the distribution, so we are moving in that direction, so the velocity in that direction, so if v times the partial derivative of u is positive, then we want to change that particular coordinate. So these switching rates, the ith switching rate determines when are we going to switch in the ith coordinates of the velocity vector. Okay, so here's an example. So we have a banana-shaped target distributions in 2 dimensions. So you can see here's the peak of the distribution. Here is my initial position and velocity. We're moving in the top left direction. And this is then how the process starts to move, and it moves quite far out into the tail of the distribution. But that's okay because it can also come back from there, and that's one of the advantages of these processes, is that they can quite easily explore the tails of a target, so it can move back and in this sense explore the distribution. And this is really to give you an idea of what the trajectories of this 2-dimensional zigzag process look like. And you can run it for a much longer time and you will explore this target distribution. Okay, so this describes the multidimensional zigzag process. So how, and we have talked about conditions so that it has the correct stationary distribution. So, but just to be sure, what does it mean? Well, if we now simulate, just make one simulation of that process for until some time horizon capital T, so continuous time process, what we call the ergodic average, the time average, converges to the space average, just as it would in discrete time MCMC, but then you would have a sum here, and now we have an integral. And so integral may look complicated. How can I evaluate this integral? But remember that x here is just moving in these directions, so it is piecewise linear. The velocity is piecewise constant. So the trajectories themselves are very simple, and maybe I can decompose this integral in an integral from one switching time to the next switching time, and so on. Yeah, so depending on how easy to evaluate then this function h is, maybe if it's a polynomial, for example, I can evaluate this integral explicitly, or if it's a sine function or a cosine function, lots of functions, I can evaluate this integral explicitly. And it's not really a problem, but maybe it is a problem for your particular use case. An alternative approach is the second one here in this display. So the first approach I mentioned is, as I just described, I can evaluate this integral analytically, or maybe numerically. I can also just discretize my continuous time trajectory, look at fixed time steps of that continuous time trajectory, and then actually my samples just behave as samples from a discrete time Markov chain with still the correct stationary distribution. Okay, one thing that I have to warn you about if you start using this, that it may be tempting to just store the moments where the process changes direction, the switching times. And if you don't think about it, you might be tempted to use these as samples of your Markov chain and treat them as in Markov Chain Monte Carlo. But of course, the moment that you switch direction, often it happens in the tail. And when you look at, suppose, just going back to this example, if I only store the points where I change direction, they only happen in the tail of the distribution, and they are definitely not, they're going to be biased samples. They are absolutely not from the correct distribution. So it is important that you realize that it's really the stationary distribution of the continuous time process that has the correct distribution. I hope it makes sense so far. No questions? No?
All is clear.
Okay, thank you. Then I mentioned one-dimensional zigzag process and multi-dimensional zigzag process, and they appeared more or less simultaneously with another sampler in the statistics literature, and the other sampler is the Bouncy particle sampler. So and it is almost the same idea, but different, in the sense that what happens now is that we still have a multidimensional target distribution on a d-dimensional state space, but our as a velocity space, we now also take r to the power d. And instead of having a uniform distribution over the velocities, which I didn't mention that explicitly, by the way, but it's written somewhere. Really, let me mention that this process has the multidimensional zigzag has a stationary distribution in position and velocity space, and in the marginal distribution in the position space is exactly your target distribution that you want, and in the velocity space it's just a uniform distribution over all the possible velocities. Okay. And now for this other sampler, the Bouncy particle sampler, it has almost the same thing. So the marginal distribution in the position space is your desired target distribution, and in the velocity space now it is a normal distribution. And what it does, without giving too many formulas, this plot is from the Bouncy particle paper. It moves. Here in the background you see a standard normal target distribution as an example. It moves until some random time, which is determined by, again, the log density function. And when it changes direction, it just bounces off where you could say you take a tangent plane to the contour of your target density there. So you see here the target, this contour line would be all, this tangent plane would be almost horizontal in the picture, and you bounce off that tangent plane. And here again, you have a tangent line to the contour. It's not exactly vertical, it's a bit skewed, but you bounce off that tangent line in this case. And but for the bouncy particle sampler, what would happen if you just do only these type of moves? In this example, it would start circling around the origin, and it would never be able to actually reach the origin. This is one of the ways that you can see that the bouncy particle sampler suffers from some reducibility problems, and that's why, just like in Hamiltonian Monte Carlo, you need to refresh sometimes the velocity. So at some independent rate, lambda refresh, this rate, constant rate, you refresh the velocity. So you draw a completely new velocity and you start moving according to that one and start bouncing according to that one. Okay, that's the bouncy particle sampler. Then I'd like to mention more recent sampler that we worked on is the Boomerang Chamber. Okay, so this is what you can immediately tell from this picture. What is the difference? That now the difference is that the trajectories are not constrained to be linear anymore. They are not along the velocity. So the velocity in particular is not constant along the trajectories, but it's changing, and it's changing in a very simple way. Third bullet, you see here the velocity is changing like this. So x is changing according to the velocity, and the velocity is changing according to the position x. So this is, we could call it a harmonic oscillator. And what it does is it preserves this reference measure in x and in position and velocity coordinates. It preserves any Gaussian reference distribution. So that's a little bit the idea here, that by just following the dynamics, you're already targeting a normal distribution. And so if your density relative to a normal distribution is maybe very well behaved, then this means you don't have to switch so often anymore, because the switches only have to take care of this part. Okay, so you already see it here. This is the reflection rate. It depends again on the derivative of the potential function and the velocity. It's just like the one-dimensional zigzag, but now it's the multi-dimensional version. But so, for example, in the simple case where u is 0, where your target is actually this Gaussian distribution, there will be no switches. The switching rate will be 0. And if u is or the derivative of u is very small compared, if the derivative is very small, there will be very few of these reflections. So that's the motivation essentially for the Boomerang sampler. That's relative to if u is you potentially have fewer reflections because maybe your target distribution is close to a Gaussian. And why a Gaussian? Maybe two reasons. When you have a lot of data, you may be aware of the Bernstein von Mises theorem, which tells you that your data will be, your posterior distribution will be approximately a Gaussian. Or also in infinite dimensions, we can actually define this Boomerang sampler in infinite dimensions, because Gaussian distributions do exist in infinite dimensions. Whereas if you think about bouncy particle sampler in zigzag, the reference distribution is just a flat Lebesgue measure, if you want, and that's not defined in infinite dimensions. So the Boomerang sampler gives you a way to define samplers in infinite dimensions. And maybe you're not interested in infinite dimensions, but it also tells you that this sampler potentially behaves well in high dimensional settings. Okay, so that's then in one slide the Boomerang Chamber. Also, again, we have to refresh to have that the sampler is irreducible, that we reach every part of the state space. It's, yeah, so you see here both refreshments and reflections, and you see that comparably they in this simulation they happen at almost the same rate, and the process, well, seems to explore this target well. Okay, then so that's the basics of what are piecewise deterministic Markov processes. What is it, and what is the zigzag process? Okay, so all these processes are examples of piecewise deterministic Markov processes, and they all share this property that I'm going to talk about next, and that's well, it's about how to simulate them, and that's how can we use that to our benefit in subsampling. So there we go. So here, suppose we're back to the one-dimensional case. Think about zigzag. We are moving velocity with velocity +1, let's say, and we start at the origin of this plot. So we are looking in the direction, the positive x direction, and this is what our derivative of u looks like in that direction. So this means that the switching intensity is then given by this formula, right? It's the maximum of 0, and because the velocity is +1, here will be the velocity, but it's +1, so this is our switching intensity, and it will be this function. So okay, but how can I? This is actually a difficult object already to work with. How do I simulate a random time that switches according to this kind of piecewise differentiable switching rate? Well, this is the trick that we use. We use the concept of Poisson thinning. So we find some upper bounds. You can any upper bound is fine, but it needs to be above your switching intensity, and you want it to be simple. You want to be able to do explicit computations with it. So how do we use it? We simulate a random time according to this upper bound. Okay, so there comes in the condition that I mentioned, that's why we want lambda, this upper bound, to be simple function, because I really want to be able to explicitly compute everything here. I want to be able to integrate this, and I want to be able then to use those values to compute, to simulate such a random time t. And this is possible if maybe you're familiar with the inverse CDF technique, as long as you can explicitly compute the cumulative distribution function and you can compute its inverse. Well, by plugging in a uniform random variable into the inverse CDF, you can actually generate random variables from the distribution. So that's what you do here. You need to be able to compute this. This is 1 minus the distribution function, and then you want to be able to invert this function, and then you can actually simulate capital T from this according to this upper bound rate. But it's not the correct rate. So how to correct for that? We accept the proposed switching time with a certain probability, which is simply a very tractable computation dividing the true rate by the simulated rate. And then the question, what do we do? Is it on the slide? No. What do we do if we don't accept the simulated time t? Well, it just means that apparently we are not switching there. So we move until this position and we iterate from this position forward. So we kind of have wasted a computation because we are not switching there, but at least the process moves forward, and in that sense, at least we move when we do this Poisson thinning approach. Okay, so that's essentially how we are computing exactly those the true switching times. So I'm not giving many proofs. I also, without proof, I claim that this is the correct switching rate, and now without proof, I'm claiming that this really has the correct switching intensity that we want. But now we're going to use that to see how we can use subsampling. So suppose that my potential function is an average of 2 functions, and already it's good to be aware. So why this? Think about Bayesian computation, where you have many independent observations, and maybe it will be a slide later. Yes, so I'm skipping ahead a little bit. So here you see in Bayesian computation, if you have many independent observations, then this is what your essentially your posterior distribution looks like, ignoring any prior distribution. But you see that it's multiplicative in those independent observations, of course, by independence. That's why you get the sum in the exponent, and that means that for the negative log density, you can write it as a sum, or equivalently as an average of several of those potential functions. Okay, so that's why we're interested in writing our full potential function as an average or a sum of potential functions. So here is an example. Well, the black thing is our objective that we want to simulate according to this potential function, but pretend we don't know it and we only know these its terms, the terms that make it up. So both of these terms have their own switching rates, if you want. And now the procedure would be that we find an upper bound, but it should be an upper bound for all of those switching rates. So now there are 2, but imagine that there are n of those. So they can have various shapes, but you want to have an upper bound that is above all of those. The procedure is the same. I draw a random time t according to my upper bounds. Now, then I randomly select which of those random components I'm going to use. So I randomly select, maybe I'm going to select 1. I flip a coin, and it turns out that I'm using U1. So it means that with this relatively high probability, namely this switching intensity divided by the upper bounds, I'm going to accept. And if I would have randomly chosen U2, then I would accept with probability 0, because the actual switching intensity there is 0. And the funny thing is that this procedure has exactly the correct stationary distribution. And when you look at it, notice that I only have to evaluate the switching intensity of the ith of this random choice that I make. So here I have 2 components, but my computation depends on being able to bounce all those components uniformly. But then I only compute the acceptance probability depending on the random term that I choose. So that means that at every step of my algorithm, so here I have n steps of my algorithm. Well, usually without subsampling, I would have to process all the data, because the switching intensity depends on the target. All the data is in there. But now with subsampling, every iteration just depends on evaluating one component of the data, the randomly chosen component of the data. So in terms of the efficiency per iteration, I gain a factor n. So you could say the efficiency of each iteration doesn't depend anymore on the size of the data. So that's a pretty significant improvement, and you do not lose correctness of the stationary distribution. So this is another thing that I'm not proving for you, but yeah, the stationary distribution is still correct. There is no, and this is different from, maybe you are familiar with other stochastic gradient algorithms, and most of you will probably be familiar with stochastic gradient descent, but that's an optimization algorithm. And we're talking about Markov Chain Monte Carlo here, but there's something similar. Stochastic gradient Langevin dynamics is an algorithm you may have heard of, and it's an algorithm where at every iteration you move in a random direction, but the randomness also obtained by choosing a random subset of your data. The point of this SGLD algorithm and other similar methods is that this randomization, this random stochastic gradient you're taking, the algorithm will be biased for that reason. It will not be a correct algorithm anymore. Asymptotically, it will not have the correct stationary distribution. And this is different. Here we still have the correct stationary distribution. Okay, now it's not so important what's written on the slides, but maybe I should explain it by this. You're looking at this slide. I mentioned the requirement that the upper bound needs to be upper bound for all those individual switching rates. And this is the thing that makes it a bit problematic, because the thing is that this upper bound is going to increase as n grows, as your number of observations grows. And also, by the way, you have to correct for the fact that U is actually an average. So this blows up the individual contributions, U1 and U2, by a factor n. So they are not the original terms, but they are n times the terms in this expression. So might be a bit confusing. The point is the switch. If you apply the subsampling method without naively, the switching intensities themselves become larger by a factor n. So what you win by having efficient computation at every iteration, you lose because you are switching more and more often, and you are making smaller and smaller steps in your state space. That's at a basic level what's happening. And so what you win here, this improved efficiency, what I write here, actually you already lose immediately because the switching intensity is much higher, the effective switching intensity. And this is then something you can correct for by applying control variates. It means we pre-process the data, so we find a point x star which is close to the mode of the posterior distribution, and we use that to have a better approximate switching intensity, a better random switching intensity. So you see here in the expression for the switching intensity, I correct for what's happening at the mode of my target distribution. So I'm talking about the mode, so I'm talking about a situation where already there is some posterior contraction. So maybe we have, and we need to do some pre-processing to find the mode of this distribution. Okay, but in this case, with this control variates, actually we can recover the original speed of the zigzag process. So what's happening in the picture is This is zigzag without subsampling on a two-dimensional logistic regression problem. So you see its trajectory, and every pink dot is one gradient evaluation, and every gradient evaluation consists of 100 observations. And now we're doing subsampling, and this is what's happening. So you see that the switching rate becomes larger, and before that reason, there will be many more switches. The process also behaves more like a diffusion process. Actually, it's something that you can show mathematically, that it will be more like a diffusion process. But that's undesired. There are more switches. Your process is moving slower, and it takes more effort to compute it. So with these control variates, now we have full subsampling, and still we are at every, well, this is an equivalent of a gradient evaluation, the distance between the pink dots. We are moving big distances. And yeah, so we really gain this order n in efficiency at the cost of having this pre-processing step. So I hope that makes sense. And here is then also, like, quantitatively, how does it work? This shows the result for comparing different algorithms as the number of observations grows in a logistic regression example. That's effective sample size per epoch. Epoch is I consider to be one gradient evaluation. Effective sample size of all these algorithms is constant because that's we are winning some, we are losing some. The process will have a higher rate, but also the distribution is more concentrated, and these effects cancel. But the zigzag with control variates, actually the number of effective samples is increasing in this number of observations. And looking at it differently, instead of comparing per epoch, but looking at effective sample size per computational, this is really wall clock time, seconds. We see that all these algorithms are performing slower as the number of observations grows. Whereas for zigzag with control variates, it's really approximately constant effective size per second. And this is comparing to some zigzag algorithms, but also to a non-zigzag algorithm, Mala algorithm, Metropolis adjusted one-to-one. So a Metropolis Hastings algorithm also has this property that its efficiency is decreasing as the number of observations grows. All right, so that's my discussion of subsampling. I see that I've already spoken for 45 minutes. So what?
Yes, you may you have like 8-9 minutes. Yours, please.
Okay. So then I think that should be fine. Thank you. So yes, the final part of the talk is can we use this for distributed computation or federated computation? So I mean here that well, federated learning, it's a machine learning technique. This is taken from Wikipedia. It's a machine learning technique that trains an algorithm across multiple decentralized servers holding local data samples without exchanging them. Okay, so there is some server, there are some local workers. The local workers are aware of maybe the statistical model, but each of them have their own data to which they want to fit the model or do some computations, but then they communicate it back to the server. And the goal is that the server combines all this information and combines it in the correct way. But how can we do that in Bayesian computation? How can we do it in MCMC? It's not so clear if every server has its own, every worker here has its own data. It's, well, it's a naive MCMC implementation would generate samples from the wrong distribution at every worker, and how to combine them, maybe some weighted average, but what weight should we take? It's not clear, and so far there exists no algorithms that can do this. And why do we want to do this? Two things to keep in mind. We might just want to not share our data, to have privacy of the data. Every worker, every node on this graph doesn't want to share their data because it's privacy concerns. Or we maybe want to gain some efficiency. Maybe we have CPU power at every worker, and we want to use it in the best way possible to have as fast as possible an algorithm. Okay, so well, can we use Piecewise Deterministic Monte Carlo? So we have our full posterior distribution pi of x, and it's this multiplication of these local likelihoods. So we want, in the end, a method that generates samples from this posterior distribution, and the workers do not have to communicate their data. So I have already introduced Piecewise Deterministic Monte Carlo in the first part of the talk. So very generally speaking, and this is a way to think in general about Piecewise Deterministic Monte Carlo, we have some deterministic dynamics, a jumping intensity, and a jump transition kernel. So the deterministic dynamics, when do we jump and what happens when we jump? And here's the zigzag again, one-dimensional zigzag. I've talked about it, and here is also the switching intensity that we want. This is the switching intensity that we want in a one-dimensional zigzag to have the correct stationary distribution. Okay, and then I said that okay, if we then take this choice of switching intensity, then actually we satisfy that condition, and this is the one-line proof of that. If we plug it in, so what is the switching direction in the +1 direction? It is the positive part of the derivative of u minus the switching direction in the negative direction. It is, well, the positive part of minus derivative of u, in other words, is the negative part of the derivative of u. And adding and subtracting the positive and negative part of anything gives the original thing. So ignore this extra dash there. This is just the derivative of u of x as you would want it to be. But now suppose that we take lambda m. I didn't write it on this slide, I see, but exactly the same thing for every machine. Every worker computes this for their local data. So for um, their own contribution, their own information encoded in their local function um. Okay, so you then have this, and the effective rate that we're going to use is summing over all those switching intensities. So just taking the sum over all these switching intensities, and if you then compute this difference as we want in the condition for correctness of the stationary distribution, this completely, well, it still works in the same way. This summation over the machines distributes over the computation I did earlier. So what we get here is a summation of prime, which shows that the switching intensity for federated learning will have the correct stationary distribution. So so here is the switching intensity. As I said, it's the usual one, but only applied to the nth data. And so this, if we add all just try to explain that if we add all those switching intensities, then we get the correct stationary distribution. So that's what we want to simulate: first switching time according to that rate lambda m, but the sum of all of these. This will give a correct algorithm. And by the way, it's good to know, this is exactly the trick that we're using in subsampling. This is also why subsampling works. Okay, but what we see here is a sum of rates, and if you have some knowledge of Poisson point processes, you realize that this is just a superposition of Poisson point processes. So what we can also do is we can simulate capital M random times according to these individual rates, and just take the minimum, take tau to be the minimum of those, and then tau will have exactly this distribution. And this is exactly, as I argued before, this will guarantee that the switching time tau, and using this iteratively, gives you a process with the correct stationary distribution. But this computation you can do locally on any machine. So this is then the algorithm. You start from some starting condition and a time 0. Locally at every machine you compute your switching time. Every machine proposes a time to switch direction, and then the server, so this is communicated to the server, this random time tau m communicated to the server, and the server decides which is the first time that is proposed. This time we're going to switch, and there we go, we make the switch. So we move further along until time t plus the simulated time. We move a position further in the current direction, and we change direction after that time tau. So that's the algorithm in a nutshell, and it works, and it has exactly the correct stationary distribution. Okay, we can talk about computational efficiency, and essentially what I've already said about subsampling is also true for this, is that if you do it naively, then you distribute your data among several machines. So in that sense, it's going to be more efficient, the computation locally, but also the effective switching rates will become larger by actually a factor m to the 1/2. So that means that you are moving more often for the same amount of continuous time that you want to simulate, and also the process is becoming diffusive. So those two, everything combined, there is no net gain in efficiency. So that's kind of disappointing news. But you could also call it good news if you think more from the privacy point of view. Okay, so we can distribute our data amongst machines. Every machine does their computation, and we can at essentially the same efficiency as before compute our Bayesian posterior distribution, our samples from that, without loss of correctness of that stationary distribution. Okay, and then in the paper that we worked on, we also proved some. So how much privacy really do we have with this method? So I will not go into details because of time, but you can quantify privacy of algorithms using the framework of differential privacy, and there's some definition saying that what if I change my data a little bit? How does it affect the outcome of any of my algorithm? And it should not be too much, because if it does affect your output, if a single data point really affects the outcome, then some attacker might be able to read from the output of the algorithm what was the data. So, and then we show for our zigzag algorithm, our federated zigzag algorithm, that indeed we do have differential privacy. So this is a long theorem to read, but basically under reasonable conditions on the switching intensity, we do have indeed differential privacy of the computation of the random times. And that's what I wanted to talk about. I hope it was clear, and here are some references. Thank you.
Thank you very much, Joris, for the very nice talk. Are there any questions for Joris?
Perhaps I can start with a simple one. Presumably, can you be having discrete parameters with the? I mean, I saw that it's all based on differentiation, right? Can you possibly include sort of discrete parameters, or you're going to end up with like discontinuous likelihoods and stuff?
Yes. Yeah, this is related a little bit to the history of how I ran personally into the zigzag algorithm. Is that I looked at the discrete algorithm. This was actually for a statistical physics problem, and also there people were looking into these algorithms which have some sense of direction or momentum. I was looking at the algorithm which we called lifted metropolis Hastings. I didn't call it that. Other people called it that, invented that. But I was trying to understand how does it behave, and then by looking at a scaling limit, I ran into I found the zigzag process. So the order was the other way around, if you want. We started with this discrete time, non-reversible algorithm, and then discovered zigzag process. So yes, it is possible, and that's maybe something to look into. This topic of lifted metropolis Hastings. It's also called Gustafsson algorithm. I forgot for a moment the name, but yes, they are there, and essentially it's the same, but you have some velocity and you make discrete jumps according to that velocity, and at some points you might want to change direction. But yeah, it always depends on that. There needs to be some velocity, I think. Some sense of direction in your state space also.
I see. Yeah, thanks.
Any other questions for Joris? Can I have a quick one, Joris?
Sure.
Are these methods applicable to cases where you have multimodality in the posterior? Do you have any actual assumption regarding that the posterior is unimodal or not?
So no, there is no such assumption. I've been very hand-wavy about what you actually need, but it's really true that to design a process it's very robust in the sense that to design a process that has the correct stationary distribution, you really only need that you can define the switching intensities, and this can also already be in a very weak sense. So absolute continuity of U is already sufficient. In other sense, it doesn't even need to be differentiable everywhere, I think. Is that correct? Well, no. Okay, now you want continuous differentiability of U, and then you will be able to define the switching rates, which have the good property. So in particular, multimodality is fine. Of course, you can start worrying about convergence of the algorithm. And then initially we thought, okay, this momentum is good. It's good to have this momentum. It will make it easy to move from one mode to another. And we did some theoretical attempts at quantifying this. And there you see like only a very, very minor benefit. But okay, and in practice, it's just difficult. You can look at one example, but then you don't know how it does for another example. I think in general, if you're able to implement it well, then these algorithms can be definitely competitive in multimodal situations. But this is another complication with multimodal, is that it becomes a bit difficult to, as I mentioned, we need these upper bounds, and this is easy if your target distribution is easy, and it is difficult if your target distribution is complicated. And in general, let me mention one. If you have a bounded Hessian, so if the log posterior is a bounded Hessian, then it's straightforward to find such an upper bound that you can work with, and so then you could easily apply this algorithm to that situation.
Nice, I see. That's really interesting. Are there any other questions?
Perhaps kind of like a related one. I mean, I was thinking, you know, if you have a practical problem, you have to somehow tune this or select the optimum, like these bounds, for example, that lambda. Is there a kind of like a guide or how you can go about, you know, because presumably there is an efficiency gain about not being too far away from the, I don't know if there is a...
Absolutely, yes.
Yeah, do you see what I'm wondering, like the practical balance of selecting these? Is there a guide perhaps, or?
Yes, well, this is really important question, and it's not so easy to answer. So in the paper that's also here is the link. We propose an approach, and so that really depends on having this bounded Hessian. But even then, for example, if you have a heavy-tailed distribution, a Cauchy distribution, then you can actually choose. Maybe I want such a bound that is locally close to my switching intensity, but you can also have a constant bound, and it also works. And then it becomes kind of challenging question, which one is better. And it's hard to compute analytically which one is better, and it is, well, the problem with simulations is always you know it for one case, but you don't, what insight does it really give you? So that's just a challenging question, but at least again, if you have a bounded Hessian, there's kind of a standard way to do this. That at least works, and that you locally have upper bound that's close, and so as you said yourself, that will be locally efficient. Only when it starts deviating a lot, then you might lose this efficiency.
Great, thanks. Yep.
So I guess if there are no other questions, we can thank Joris once again for this interesting talk. Joris, thank you very much. And
thank you for the invitation. I hope it was understandable for everybody. And and
thank
maybe
you.
we meet another time in real life.
Sorry?
Maybe we meet another time.
Sure. Let's hope that we can meet in person in the near future. I think that the last we had met once some years ago in Manchester.
Yeah. Yes. That was when I gave a talk with Magnus.
Yeah, exactly.
Okay.
Yeah. So take care, all the best, and thank you very much once again.
Okay. Thank you. Bye.
Thank you.